Hello, thank you for watching this video. So in this video, I'll be doing question 7 of May, June 2023, question paper physical science, paper 1. The topic is the electrostatics, right? So let's go. Question 7 read as follows. 2-point charges X and Y are held 0.03 meters apart as shown in the diagram. Point X has the charge of minus 7.2 times 10 to minus 9 coulombs, while charge Y has a charge of 7.2 times 10 to the minus 9 coulombs. Let's read this thing again. 2-point charges X and Y are held 0.03 meters apart as shown in the diagram. Charge X is minus 7.2 times 10 raised to minus 9 coulombs, while charge Y is positive 7.2 times 10 to the power negative 9 coulombs. So we have these 2-point charges X and Y, right? You are told that the point charge X have a charge of minus 7.2 times 10 to the minus 9 coulombs, and charge Y have a charge of positive 7.2 times 10 to the power minus 9 coulombs, right? And we're told that these two charges are held 0.03 meters apart. These 2-point charges are 0.03 meters apart. That's what they're telling you. No problem. So they're saying state Coulomb's law in words. They want you to state Coulomb's law in words. What is Coulomb's law? So Coulomb's law, right? 6.1. They want you to state the Coulomb's law. 6.1. You know, by formula, Coulomb's law is this. K, Q1, say in this case it will be Qx, Qy, all over the square of a distance between them. So, Coulomb's law is a law which states that the electrostatic force between 2-point charges, which is the electrostatic force X exert on Y and Y exert on X, right, is directly proportional to the product of the charges and inversely proportional to the square of a distance between them. So what this thing says, it says that your electrostatic force that the charges, the 2-point charges, exert on each other is directly proportional to what? To the product of the charges, Q1 times Q2. And the same electrostatic force is inversely proportional to the square of a distance between these two charges. That's Coulomb's law for you. So Coulomb's law states that the electrostatic force between 2-point charges, or the magnitude of the electrostatic force between two charges, is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. So let me write it down. Let me try to write it down at least. So Coulomb's law states that the electrostatic force, between, or by that electrostatic force, we're mostly referring to the magnitude, right? We're interested in the magnitude. The magnitude of the electrostatic force between 2-point charges, right? Between 2-point charges is directly, which is this part, proportional to the product of the charges and inversely proportional to what? To the square of the distance between them. To the square of the distance between their centers. So this distance that you can see here, is the distance between their centers. So the magnitude of the electrostatic force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between their centers. That's Coulomb's law. Is this law here? No problem. Go to the next one, which is 7.2. 7.2. This one is finished. 7.2. This one is 7.1, not 6.1. So, what are they saying in 7.2? They are saying, draw the net electric field patterns due to point charges. So they want us to draw electric field patterns due to these point charges. So, this one, okay. This one is a negative one, right? And the other one is positive. So, you know, electric lines, field lines come out of the positive one towards the negative one. So, I'm going to do like this. The direction is this one. Have another one there, same direction. Another one there, same direction. So you have one exiting at the back and coming all the way back to this one here, right? So you can have one goes down here, same direction, this way, right? So you can have others going to that direct, oh sorry, they should be coming in, right? And they are coming out of this negative one, out of this positive one. So this, yeah, something like this will do the work, because you can see their electric field lines are coming out of this positive one to the negative one. So this one that you can see is this one over here. This one that you can see is this one over here. And this one that you can see is that one that comes out at the back, go around and come to this side. These are your electric field lines between these two charges. I remember in one of my past papers, I drew these things incorrectly. They were very wrong, you know. But yeah, I'm happy that I rectified that mistake on this one. So let's move. We go to 7.3. 7.3. They're saying calculate the magnitude of the electrostatic force that Y exerts on X. So they want us to find the magnitude of the electrostatic force that Y exerts on X. I said that the magnitude of the electrostatic force, right, between 2 point charges is directly proportional to the product of their forces, of their charges, and inversely proportional to the square of the distance between them. So, when you talk about the magnitude of the electrostatic force between those 2 point charges, right, you are talking about the force that Y exerts on X and the force that X exerts on Y. So, these are forces that, so the force between them are the forces they exert on each other. So, when you say the magnitude of the electrostatic force between the 2 point charges, we are talking about the force that these charges exert on each other. So this is to find the magnitude of that. If you find the magnitude exerted by Y on X, if you find the magnitude of the electrostatic force exerted by Y on X, and you find the magnitude of the electrostatic force exerted by X on Y, it should be the same. The magnitude should be the same. But the direction will be the only difference. So, but now, they want us to find the magnitude of the electrostatic force, which is easy. So you say, okay, the electrostatic force, the magnitude of the electrostatic force is equal to K, Q1, Q2, all over R squared. And it's the square of the distance between them. So you want the force, here's your F. Q1, or your K, Coulombs constant, which is 9 times 10 to the 9, times Q1. Q1, the magnitude of the first charge is what? Is 7.2. You only put the magnitude, which is 7.2, times 10 to the minus 9. Q2 is also 7.2. 7.2 times 10 to the minus 9. All over the square of a distance between them. What is the distance between them? The distance between them is 0.03 all squared. So what you get here is the electrostatic force between them, which is the force that they exert on each other. By finding this, you also found the force exerted by that Y exert on S, which is the same thing. So let's punch that. 9 times 10 to the power 9 times 7.2 times 10 to the power 9 minus 9. Right? Just punch this. All divided by 0.03 all squared. So the magnitude of the electrostatic force, I'm trying to put it in scientific notation, right, is 5.18 times 10 to the minus 4 newtons. So this is the magnitude of the electrostatic force between the 2 point charges. So this force is the magnitude that X exerts, the magnitude of the force that X exerts on Y and Y exerts on S. So you can say, therefore, you can say your Y exerts 5.18 times 10 to the minus 4 newtons on what? On X. That's it. This one is also finished. I'm going to use a navy color now, or blue color. So we're done with this one. Now we're going to go to the next one. So it seems like I would have to draw something, because yeah, or what I will do, I will clean this so that I can have all the space in the world. So I'll clean this because we're done with 7.1, which is that, 7.2, which is this, 7.3, which is this. We're left with 7.4 and 7.5. So let me clean the board, then we'll do those. Okay, so now I've drawn this diagram, right? So I'm just going to read the statement and then we go. They're saying now, a third point charge Z of unknown positive charge is positioned 0.01 meters to the left of point X on the line joining point charges X and Y as shown in the diagram below. Let me read this thing again. They're saying a third point charge Z of unknown positive charge is positioned 0.01 meters to the left of point charge X on the line joining point charges X and Y as shown in the diagram. So, if you remember from the previous question, we were given X and Y, right? No problem. So now, on the same line that X and Y are on, another point charge Z is placed to the left of X 0.01 meters away from point X. That's what they're telling us. That's all. What they tell you is that this, what you know about this one, it's just that it's positive. But you don't know its sign. You don't know its magnitude. You don't know the magnitude of this charge. So what they're telling you, on the first question, you're given X and Y, right? That's all you're given. And these are the respective charges of those charges, X and Y. And then now they're telling you another charge now, Z, is placed here, which is 0.01 meters on the left of X. That's what they're saying. That's all they tell you. So no problem. Now let's do 7.4. 7.4 read as follows. Draw a label vector diagram to show all the directions of the electric fields at the point where X is positioned. Let me read this thing again. They are saying draw a labeled vector diagram to show the directions of the electric fields at the point where X is positioned. So they want us to draw a vector diagram to show the directions of the electric field at X, right? So this is 7.4. So they want us to draw the the vector diagram for all the electric fields at point X. So if you are point X, you are sitting here, right? Your point X now. Here is X, you are sitting here. What is happening to you? So there is a positive charge on the left, right? There's this positive charge on the left. You know, if a positive charge is sitting on its own, here's a positive charge sitting on its own, you know that the electric field lines are radiating out of this charge, right? This is how the electric field lines are on a positive charge. If it's sitting on its own, the electric field lines are all going outwards, right? So, if this is a positive charge, the electric field lines in all directions, right? Like that. But, if you look at this one here, let's say your X is sitting here. Your X will if your X here, the electric field felt by X due to this charge will be in that direction because it will be filling this one over here. So if your X was sitting here, right, and there's this positive charge that is radiating out in all directions, you will feel the electric field, this electric field that is to that side. So if your X sitting here, you will feel an outward electric field of Z to that direction. So it will be like this. So this is an electric field of what? Of Z on X. Right? This is the electric field of Z on X, because like I said, with the Z is positive. So again, if your X sitting here, right, these have field lines going all directions, like I said there. So if your X, this one will be in that direction. So here is it. And this one is similar to this one is here, this one as well. But the difference is X now is on the left, right? So X is on the left of Y. So if this is your Y now, I'm not using it Z, this is Y now. Here's Y. Actually, yeah, this is Y, this is your Y now at this point. And X is on the left of Y. So X is chilling somewhere here. So you can see that the field lines are going out in all directions. If your X, the field lines that you'll experience from Y will be towards that direction. So the electric field at X due to Y will be in this direction. So this is the electric field of Y on X. So this is how I'll draw it. And I'm done here. So I'll go to 7.5, the last question. So now we're doing 7.5. They are saying the magnitude of the resultant electric field at point where X is positioned is 4.91 times 10 to the 5 newtons per coulomb. Calculate the magnitude of charge Z. Let me read this thing again. They are saying the magnitude of the resultant electric field at point where X is positioned is 4.91 times 10 to the power 5 newtons per coulomb. Calculate the magnitude of Z. So they are telling you at this point here, the net electric field is what? Is 4.91 times 10 to the 5 newtons per coulomb. At this point, the net electric field is that. But you know that an electric field is a vector. But we're not told the direction. We're not told the direction of this electric field. So, I would say it doesn't matter which side you push it into. As long as all your calculations will be consistent, it should be fine. So, just to make things a bit easy for me, I'll do this. I'll draw this coordinate system, right? And say positive, positive. So all electric fields to that side are positive, and all electric fields to the side are negative. This is what this thing will do for me. All electric fields to that side are positive, and all our electric side to that side are negative. So what I will do is, I will take my net electric field to go to the right? I will take my net electric field to go to the right, so it will be positive. So I'll make my electric field positive. and this one will be positive, and this one will be negative. So I know that my E net is equal to, how will I find it? I will say the electric field of Z on X plus. So here again, my net electric field, I said that I'm taking it to, I'll assume that my net electric field is going to the right? So I'll take it as positive to be consistent with my coordinate system. This electric field is positive and this one is negative. So my net electric field in net is equal to the electric field of at X due to Z minus the electric field at X due to Y. Right? No problem. Because this one is positive because it's going to that side, and this one is negative because it's going to this side. No problem. So let's go. So E net is equal to is an X minus EY X. Right? So we know that E net is equal to this, which is K Q what? QZ charge Z, right? All over. Let's say this is R1 squared. So this is R1 here. Let's say this is R2 minus K Q X all over R2 all squared. It's R2. No problem. So what can we do? We can say, okay, we can substitute here and say, okay, 4.91, right, times 10 to the 5. It's positive. Like I said, because it's going to the right, I assume that it's going to the right. It's equal to K, which is 9, times 10 to the 9, times QZ, which is what we're looking for, all over R1 all squared, which is 0.01 all squared, minus 9 times 10 to the 9, times QX, which we're given to be 7.2, times 10 to the minus 9, all over R2, which is R2 is this one here, which is 0.03 all squared. This is what we're trying to solve. We can take this to this side, or maybe I'll try to find numbers first. So what we have is 4.91. 4.91 times 10 to the 5 is equal to, the answer to this, let's patch that and see what we get. Patch 9 times 10 to the power 9 over 0.01 all squared. 9 times 10 to the power 9 divided by 0.01 all squared. So what do we get? We get 9 times 10 to the power 13 QZ, right? QZ, which is this part, minus, hash this, all of it. So, times 7.2 times 10 to the power minus 9. So we get that this is 7.2 L times 10 to the power 4. Take this to that side. So what do you have? You have 4.91 times 10 to the 5 plus 7.2 times 10 to the 4 is equal to 9 times 10 to the 13 QZ. I hope that is correct. Right? No problem. Then we add these two. So what are we adding? We're adding this plus 4.91 plus 4.91 times 10. We're adding this side to the power 5. So this is 5.63 times 10 to the 5 is equal to 9 times 10 to the 13 QZ. Divide by 9 times 10 to the 13, divide by 9 times 10 to the 13. So you get that your charge Z is equal to the answer to this. So divide by 9 divided by 9 times 10 to the power 13. So you get that your QZ is equal to 6.26 times 10 to the power minus 9, which is therefore the QZ is equal to 6.26 nanocoulombs. So these are coulombs. We're done. You can end here. It's enough. It's not the end of the world. And I hope this question does make sense to you as it does to me. Thank you for watching. Cheers.